Good day to you all. Here, We Learners Note is an online solution to encourage an effective way of education to all of your students. My name is Yarika and I am your physics teacher. Here, we are going to discuss about the motion of a charged particle in a magnetic and electric field. That is, if we are allowing a charged particle to move in a combined effect of electric and magnetic field, what will be happen? That is, what should be the trajectory of that particle, whether it will be straight line or not. We are going to check that. Let's do. That is, if a charged particle, then which are the charged particles? We have positive and negative charges. Okay, so here we are going to discuss about the positive charge particles. If a charged particle is moved in a combined effect of uniform electric and magnetic field, it will be experience a force, and that force is known as Lorentz force. Okay, so if a charged particle is moving, that is a charged particle having charge Q is moving with a velocity V, it will experience a force, and that force is known as the Lorentz force. And we can write an expression for that force as F is equal to QE plus QV cross B. This is the total force experiencing that particular charged particle while it is moving in a uniform field of magnetic and electric forces. So, if a charged particle, that is Q charge, is moving with a velocity V in a uniform electric and magnetic field, it will experience a force of F is equal to QE plus QV cross B. That is, this QE corresponding to the force due to the electric field, and this Q into V cross B represents the force experienced due to the uniform magnetic field. Okay. So, here this representation, this Fleming's left hand rule is used for finding the direction of that force. That is, the force experienced by that charged particle Q. The direction can be found out by using this principle. Okay, this is Fleming's left hand rule. For that, we have to keep our three fingers, that is our thumb, index finger and this middle finger perpendicular to each other. And you have to keep the index finger in the direction of the magnetic field and this middle finger in the direction of movement of the charged particle. Then you can see that the direction of this thumb is upward direction. What it means? The direction of the Lorentz force will be in upward direction in this condition. That is shown here. Here we can see that this index finger directing towards the magnetic field. That is, magnetic field is directing from this north field to south pole. Here you can see that this index finger is directed in the magnetic field. Okay, that is, magnetic field is directed from this north pole to the south pole. Okay, so index finger is directed in this direction, and the direction of current, that is the direction of movement of that charged particle, that is represented by this middle finger, and this thumb indicate the direction of the force, that is direction of the Lorentz force. That means the charged particle will experience a force in upward direction if the direction of the magnetic field in this way and the direction of the movement of the charged particle is in this direction. Okay. And we can see that due to this Lorentz force, this charged particle will move in a circular path. Why? Because we already know that if there is a body moving with a uniform velocity and if it experiences a force towards the center, okay, if it experiences a centripetal force, it will start to move in a circular path. It will follow a circular path. So, the trajectory of this charged particle in this combined effect of uniform magnetic and electric field will be in a circular path. It will follow a circular path. Okay. Here, this is the representation of the thing that I have discussed here. That is, we have a magnetic field here that is represented by these arrows, and this plus Q is the charged particle which is enters perpendicular to the direction of electric field and magnetic field, and it is moving with a velocity V. This B represents the strength of magnetic field. Okay, and this F represents the direction of force experienced by this charged particle, and this direction is getting from the law of Fleming's left hand rule. Okay, then next we are going to find some expression for the time period and the frequency of rotation of this charged particle, and also the radius of that rotational motion. Okay, for that we are considering the force F is equal to BQV sin theta. This force is due to the uniform magnetic field. Okay, that is equal to BQV sin theta. If theta is equal to 90 degree, this equation will become BQV because sin 90 is equal to 1. So our force become BQV. Okay, and this is the centripetal force because this charged particle is moving in a circular path. So there will be a centripetal force. The equation of centripetal force is given by F is equal to mv square divided by r. And these two forces, that is this BQV sin theta and this mv square divided by r, these two forces will be equal. That's why this charged particle is following a uniform circular path. So we can equate these two equations, that is this BQV. Here we are equating these two equations, that is centripetal force is equal to BQV. Then from this relationship we can find the value of r. Here r is the radius of that circular path. R is equal to mv divided by bq. Next we are going to find the angular velocity. It is given by omega and it is equal to v divided by r. Here v is the linear velocity of that charged particle and r is the radius of that circular path. Then substituting the value of r here, we will get omega is equal to bq divided by m. Then next we are going to find the time period of that rotation, that is t is equal to 2 pi by omega. We already studied that time period is equal to 2 pi divided by omega. Then next we are substituting the value of omega here. We will get the representation of time period is equal to 2 pi m divided by bq. Here m is the mass of that moving particle and q is the charge of that particle, b is the magnetic field strength. This time period indicates that the time required for that charged particle to complete one rotation. Then next about the frequency. Frequency is equal to 1 by t. Here we know there is a relationship between the frequency and time period. Frequency means the number of rotations that charged particle can complete in 1 unit time. So F is equal to 1 by t. Substituting t here, we will get F is equal to bq divided by 2 pi m. Okay. This represents the force acting on this charged particle and its direction of motion, that is it's a trajectory, it is a circular path. Okay, here we can see that the cross signs, this cross sign indicates the direction of the uniform magnetic fields and it directs towards the paper, into the paper, and this red lines indicates the force, that is Lorentz force, and it also represents the centripetal force and it will be acting towards the center. Let's do some activities to demonstrate what we have discussed now. For doing this experiment, we need some salt water and a petri dish, sesame seeds and ring magnets and a power supply. Let's do the activity. For that, we have to place this petri dish on this ring magnet and pour some salt water, and this petri dish is covered with some aluminum foil. This is for providing the required electric field, and we are sprinkling some sesame seeds. Okay, the sesame seeds are used for identify the motion of this charged ions. Okay, then we are connecting this negative terminal of this power source to this portion, that is to this aluminum foil, and this is positive terminal. This is connected to the positive terminal of this power supply. Here I am applying this positive terminal in this salt water. So you can see that these sesame seeds are rotating. This is due to the rotational movement of ions, charged ions in this water. Okay. Here you can see that the motion of the sesame seeds is in anti-clockwise direction. That is, the motion of these charged ions are in anti-clockwise direction. Okay, then next we are going to reverse the direction of this magnetic field. So you can see that the direction of rotation of these charged ions will be reversed. That is, it will become in clockwise direction. Let's check. Now I am reversing the direction of this magnetic ring and placing it again, and I am applying the same positive terminal in this salt water. Now you can see that the direction of rotation of the sesame seeds are in clockwise direction. This is because the charged ions of the salt water is rotating in clockwise direction. That's why. Then you can see that these sesame seeds are continue their rotation motion. This is due to the inertia property of these charged ion particles. By changing the polarity of the power supply, we can change the direction of rotation of the ions. Here we can change the direction of rotation by reversing the electric field polarity also. That is, by connecting the positive terminal of the power supply to this aluminum foil. Then we can conclude this topic as, that is, if a charged particle is moving in a uniform magnetic field and electric field, it will experience a Lorentz force. As a result, that particle will move in a circular path. That is, the trajectory of that charged particle will be a circular path. And we can see that there is no work done by this uniform magnetic field, because the direction of the motion and the direction of this magnetic field are perpendicular to each other. So work done by this magnetic force on this charged particle will be equal to 0. Dear students, I hope all of you understood what I have demonstrated here. And here we are presenting a topic in front of you in an experimental method. That is, we are doing some experiments in front of you, and we are implemented our new method, that is learn by doing method. And you can see a lot of videos in our official website, that is www.learnersnote.com. Here I am Sharika VS, your physics teacher, signing off.